This is a pressure swing distillation practice problem. It says a feed of 80% acetone, 20% methanol must be separated into 95% pure components. Key, plural. Design a pressure swing distillation system that will achieve the separation. Equilibrium data is plotted for you below. So these are all the same graphs. I've just got them together on this diagram, and then I separated them on the right so you could see them a little bit easier. The first task is to specify the operating pressures of the columns. So I've gone through and I've drawn a quick skeleton of what the process flow diagram will look like. I don't know off the bat whether or not I should send the top product or the bottom product to column 2. So we're going to work that out as we go through the problem. But the second column kind of looks as usual, but we don't know where the feed is coming from. 80% pure acetone is our feed, and that is up in this purple dot that I've drawn. And so it's on the other side of the azeotrope. So how do I choose the pressure? Let's just go ahead and assume that the first pressure is P is equal to 0.5 atmospheres. So there's a better way to do this without assuming anything, but I want to illustrate it like this. So if I've got 80% pure acetone, then in my first column, the best I can do is going to be 95% pure acetone. So I have to stay within this region of the equilibrium diagram. And I know it's 95% because that is what my specification was. So just again, in your mind, imagine that this entire diagram is rotated 180 degrees. Unfortunately, I can't do that because these plots are flattened and I can't alter them. So I'm just going to work with this one upside down. So if this were 95% pure acetone, right? So 95% pure acetone is on that axis. Then my distillate product can at maximum be azeotropic composition. And it looks like my azeotrope is maybe 73%. So the problem didn't tell me what my composition out of the top stream could be, but that's kind of looking ahead to question 2. What is the minimum composition of component A you should specify in the distillate of column 1? We have some freedom over what to choose. So let's say we go to the maximum, and we say this is 73% pure acetone out of the tops. 73% acetone. Well, the azeotropic composition is the one that's going to get sent to the second column. And by process of elimination, my second column has to be operating at the second pressure. And by the way, there's no reason why you can't have a third pressure. I'm just operating under the assumption that these 2 pressures are the only ones possible, but that is not the case. I could have a third pressure here, but I'd have to know what the equilibrium data would look like. All right, so down in the second graph where I have acetone methanol at my second pressure, P is equal to 1.5 atmospheres, my feed is going to be 73% pure, so right there. And as you can see, this is going to be the same type of problem that I had in column 1. So from column 2, if this is my pressure, then the best I can do is 95% pure acetone. And now I can get a little bit more pure, but I can't get to that pure methanol. I'm still on this side of the azeotrope. So that tells me that my initial assumption was wrong. And instead of saying that column 1 operates at pressure of 0.5 atmospheres, I know that I have to have column 1 operating at 1.5 atmospheres. And column 2 must then be, by process of elimination, 0.5 atmospheres. All right, so let's work off that. So same idea. I can still get, if this is my feed, 80% pure acetone, I'm going to be able to get to 95% pure acetone in the bottoms of column 1. And again, this is bottoms, not tops, because I have to rotate this around to get my equilibrium data on top of the y equals x diagram, as it usually is. All right, so I'm saying 95% pure acetone because that is what my specification was. And let's see, we don't have a flow rate. Okay, flow rate must not come into play in this problem. All right, question 1 is done. So pressure 1 is equal to 1.5 atmospheres. Pressure 2 is 0.5 atmospheres. Done. What is the minimum composition of component A that you should specify in the distillate of column 1? So as I said, we've got some freedom here. But in order to prevent a problem like we had before, I'm going to want to peek ahead to pressure 2 and know that I can get past the azeotrope on the other side. In other words, if I choose a distillate composition that is 75% pure acetone, and then I go up in the second pressure and I put 75% pure acetone, well, now I'm still on the same side of the azeotrope. So for question 2, I want to get to the other side of the azeotrope. Get to other side of azeotrope, but specifically other side of the azeotrope for pressure 2. So looking at what the azeotrope for pressure 2 is, it's going to be about 73%. In other words, I have to get to at least 73% or less, right? So it'd be even better if I got to 70% pure. So what's the question? What is the minimum composition of component A? It's going to be the azeotropic composition from the second column. So the answer to question 2 is it must be less than or equal to 73%, which is the azeotropic composition of pressure 2. All right, so let's not specify the exact minimum, because when you specify the exact minimum, that can get you into trouble. I'm going to specify that column 1 is going to be 70% pure instead acetone. 70% acetone, and that's going to go to the second column. Okay, suppose that the distillate composition is set to 70% acetone. Well, perfect. Looks like I specified the correct thing. If you specify N is equal to 4 stages, what reflux ratio should you use in the first column? All right, so I'm in the first column, and I've specified now that N is equal to 4 stages. 1, 2, 3, 4. And I want to know what reflux ratio I need. So I'm going to work off of this diagram. Again, I'm going to do it in my head. I'm going to flip it, but I'm going to work with it upside down. And I need to be more careful here with my dots. So feed is Z, 80%. I'm going to assume it's a saturated liquid feed, meaning that my feed line is as a slope of 1. So sketching in my feed line. All this stuff from distillation is still relevant, so please don't forget about any of that. And I'm going to do what the problem tells me and say that XD is 70%. And now I have not set a reflux ratio. It wants me to figure out what the reflux ratio is. And I'm going to further constrain that my feed is going to be located in the best place. So I need to zoom in here a little bit. All right, so any problem where I don't know what the reflux ratio is a guess and check type problem. So I've just guessed a reflux ratio there. And now my stripping section operating line is going to be where XB, which is 95%, meets the intersection of the other two. It's like I didn't get it quite on XB. All right, so ask yourself, why is XB again on the upper left? That's usually where XD is. And that's because we are working with an upside down distillation column. And now I can stage step as usual. So 1 stage, 2 stages, 3 stages, and 4 stages. That's not too bad. Whoops, did the wrong one. That's not too bad. I overshot it a little bit. So if I wanted to get a more precise answer, I'd continue to guess and check reflux ratios until I landed exactly on XB. I think that's close enough, especially for an in-class problem. So now that I've drawn the line properly, I can go through and figure out what reflux ratio that corresponds to. So I'm going to clean up my diagram a little bit. And remember that the slope of this line, M is equal to R over R plus 1. And what is my slope? It looks like the slope is, let's see, this is 76%, 0.76 minus 0.7 over my run. So 0.80 minus 0.70. And that is equal to R over R plus 1. I'm going to skip the calculation of that. That's just one equation, one unknown that you can solve for, but that is how you would solve for the reflux ratio. So again, guessing and checking what the line looks like, constructing my stripping section operating line, stepping my stages as usual, even though they're upside down, and then finally calculating what the slope is once I get 4 stages. All right, next question is what are the conditions of the feed for the second column? Because of how I've specified it with a partial condenser, and I'll show you why that's going to be useful in a second. A partial condenser is going to give me a saturated vapor feed, saturated vapor, 70% pure acetone. And so let's see where that is. Now I'm on my second column, and now I'm here, 70% pure. And now you can see why I did a saturated vapor feed. If I did a saturated liquid feed, I'm going to zoom in. Come on. If I did a saturated liquid feed, then I'm going to have a vertical feed line, and that doesn't give me much room to operate up in this area. So a horizontal feed line at least gives me a little bit. And if I had a superheated vapor line, feed line, that would be even better. So maybe I want to preheat this feed before it goes into the second column to give me a little bit more room to operate. But we'll assume that that's not part of it. Let's just say, keep it simple and say saturated vapor. We're not going to put a heat exchanger in, although you could. All right, how many stages do you need to the second column if you specify that R equals 3? So there's a couple of things we got to do first before we can go stepping stages. First thing to do is to set what our distillate and our bottoms purities are going to be. I'm constrained that I want 95% pure components. So this bottom stream has to be 95% pure methanol. In other words, it has to be 5% acetone. And now that I'm working on a right side up diagram, I think this one would make a little bit more sense, where my XB has got to be down here at 0.05. All right, now my XD, I definitely need to zoom in, but I have freedom to choose whatever I want. And it doesn't really make sense to constrain anything too crazy, but it's got to be a little bit, it's got to be in between what the feed is and what the azeotrope is. That's the only thing I could possibly do. And let's see, I need a, it's really hard to draw what the rectifying section operating line would look like, but I need a reflux ratio of 3. And in a lot of respects, it doesn't really matter what the reflux ratio is if it's so close, right? But it's got to be somewhere along this line. And I guess, it does matter because it's going to tell me how many stages I need, but it's going to be really intricate in this area. All right, so let's see if I can get something accurate here. A reflux ratio of 3 is going to be a slope of 3/4. So we can work out what this is going to look like in a little bit more detail, but a reflux ratio of 3/4 is going to be approximately a little bit less steep than a 1, so maybe something like that. So imagine what the, remember you can figure out what the minimum reflux is that I'll need to send. If I send any less reflux, then my line is going to be out this way, and I'm going to have a lot more stages. So the closer I get to this pinch point is going to be a ton more stages. All right, so once I have that point, I can then connect XB to the intersection of the other two, and then I can continue stepping stages as I usually would. So 1, whoops, that one got crooked. Just going to redraw it. 2, 3, 4, and the last one is going to be the reboiler. Oh, I made a mistake then in my other one, right? So In column 1, with 4 stages, I forgot to step off the 5th stage for the reboiler. Right, so this one is not correct. I'm not going to go back and demonstrate it again. You just need to have 5 stages. So if you caught that before I did, awesome job. That's a really good recollection of how to do these problems. So remember, 4 stages is equal to 5 steps because they're partial reboiler. Oh, and the partial condenser. So I missed 2 things, right? So in the first column, I actually have 6 steps because of the partial condenser and partial reboiler. They both count as equilibrium stages. So minus 15 points for me. If this were an exam, I would have gotten that wrong. Well, I caught it in the end, I guess. I had to go back and fix it. Anyway, how many stages do you need in the second column if you specify R is equal to 3? 1, 2, 3, 4, and a reboiler. 4 plus reboiler. All right, so that's typically how pressure swing distillation problems work. You first have to figure it out from a process standpoint of which streams go where, and it won't always be that the tops goes to the second column, or that the bottoms products are your pure components. It won't always be that one component is always in the first column. It won't always, there's no general rules other than you have to step through, similar to how I've done here, and think about it in those type of terms. So next time I want to do a practice problem that looks at a material balance, or maybe I'll give you one of those on the homework or something, or maybe not, I don't know. I have to decide what I want to do in the last couple of classes here. Anyway, thanks for watching. That's going to be all for today. I'll see you next week.